Hello students, welcome to Sarasa classes, and over here in this part of the lecture we will be discussing some more advanced problems in 1,2 dihydroxylation reaction using osmium tetroxide, and here the topic is the stereoselectivity. So now think we have been given a ene bond and there is a group out here. Okay. For the sake of simplicity, I am considering this to be as a OH group. It can be any other group also, it can be a methyl also. Now, the thing I'm wanting to say is that whenever you are using only osmium tetroxide as a reagent, okay, and you're reacting, then the osmium tetroxide will approach from the top side, okay. So the OH groups formed out here will be having a anti-relationship with this group over here, okay. However, if you use ethylene diamine, then there is a possibility of a chelation or hydrogen bonding with the allylic alcohol. So if there is a chelation with this group over here, that means now instead of coming from this side, in presence of ethylene diamine, the osmium tetroxide, that is this unit, will come from, so it will attack these lobes because it is being assisted by some hydrogen bonding happening over here by this red sphere, which is obviously my OH group. And so the OH groups helps the osmium tetroxide to undergo a 3+2 cycloaddition reaction with the alkene from this side of the lobes, and hence, so in presence of ethylene diamine, the OH groups will be disposed in this direction, that is on the same side that of the OH group when ethylene diamine is present. When ethylene diamine is not present, then OH groups are on the absolutely opposite side, that is the reverse side. Okay, so let's look. We have some group over here which is methyl, can also be an OH, that is CH2OH, and you have only osmium tetroxide, there is no ethylene diamine over here. So what we will say, the OH groups that are going to be joining on this particular ene bond are going to have a stereochemistry that is opposite to the stereochemistry of this methyl group. That is, if it is in the alpha bond, these ones coming will be in the beta bonds as shown. Okay, I hope that is clear. Similarly, obviously this alkene is having an electron withdrawing group, so it is less reactive, reactivity of alkenes. This is comparatively more reactive, so this is the one that will be undergoing reaction with osmium tetroxide. This one is in the alpha position, there is no ethylene diamine, so osmium tetroxide along with only NMO. Okay, so that means over here the OH groups will be joined, or the osmate ester will be formed from the attack from downside of the plane of this ring. That means OH groups will be in the beta bonds, not in the alpha bonds. Tetrabutyl ammonium fluoride is to remove the silyl protection over here, so OH will be formed subsequently. Okay, and the TMSOK is to remove the methyl group over here and convert this into OH. As simple as that. Next part, similar thing, our alkene is over here. Okay, the OAC group is on the alpha bond, that is above the plane of this ring, that is the cycloalkene, and we are only using osmium tetroxide. There is no presence of ethylene diamine, hence the OH groups will be disposed below the plane of the ring, that is If this is in alpha, this will be in beta bonds. So that is about the selectivity. Few more examples. Aspen tetroxide is used only. Okay. So over here, this is the alkene bond and the OH groups will be placed downwards. Similar reasons, osmium tetroxide is only used again because of steric bulk. The OH groups will be placed downwards. After this two, this is most reactive, and again there is a methyl group over here. So with keeping the stereochemistry of this methyl group in mind, these OH groups will be placed downwards. Okay. Again, bicyclic systems, a similar one we did before. This is the bridgehead. Osmium will be approaching from below the plane, not from the top side, and hence the OH groups will be placed downwards and not top. So this is the stereochemistry of the OH group. A similar reasoning can be used for the other reaction over here. Now, again we have a allylic alcohol and we are using osmium tetroxide in presence of NMO, and we have been given the choice of these two compounds 1 and 2, and using the reasons that we have studied before, we will say 1 will be preferentially the most or will be the major product out here, and 2 will be the least or the minor product out here. Similarly, over here, as we can see, another alkene is given over here and osmium tetroxide is only used. There is no ethylene diamine. So out here again we will say that 3 gives 4 as the major product, okay, and 5 will be the minor product using the reasons that we have studied before or we have mentioned over here. As you can see, the reaction of allylic ethers, okay, to diols is highly selective, giving preferentially the isomer in which the original hydroxy or alkoxy and the adjacent newly introduced diol are anti to one another. So this OH group and the diol will be anti to one another. This ethereal group or ether group with the OH will be anti to one another. Okay. Next, using the similar reason, OH groups will be anti to one another. This is obviously the next topic that we are going to discuss, which is going to be Prevost Hydroxylation, and in which if you use instead of osmium tetroxide in presence of NMO, if you use silver acetate iodine with aqueous workup, we will be getting the OH on the reverse side, or will be, if the methyl group is in the alpha position, the OH groups will be syn to this alpha methyl group, whereas in case of osmium tetroxide it is anti to the methyl group. Same thing out here with respect to this particular methyl group. The hydroxylation of this alkene will not take place from this side but from the reverse side, and if it is stop, then it will be towards the down position. Potassium permanganate is also functioning very similarly to osmium tetroxide, but the only difference between the two is that potassium permanganate is a colored solid. So there is a correction over here, it's purple in color. The permanganic acid, which is produced by the reaction of potassium potassium permanganate with sulfuric acid is highly explosive. It is basically Mn2O7, that is the acid anhydride. Okay. It is a cheaper solid. That is one big difference between osmium tetroxide and potassium permanganate. Highly water soluble. It is insoluble in organic solvents. That is another fundamental difference. Both produce syndiols. Okay. Solvents in which this can be solubilized using aqueous and benzene mixture or a phase transfer catalyst, as we will discuss, or we can use solvent mixtures like aqueous benzene, aqueous acetone, aqueous alcohols, aqueous ethers, or aqueous acetic acid. As I have said, the reaction proceeds via syn addition of permanganate to the double bond as indicated, and gives the corresponding cis diol under the aqueous alkaline conditions. Okay, that is important. Alkaline conditions are needed for syn diol preparation. If you use acidic conditions, then chances are acid will be the final product and not alcohol. So these are some of the phase transfer catalytic reagents that can be used along with potassium permanganate to carry out reactions in non-aqueous medium. So if you want to introduce the KMnO4 minus unit into the non-aqueous medium, so one can use the tetrabutyl or tetraethyl ammonium chloride, or one can use a 18 crown 6 to carry out these reactions. Next, the purple color of KMnO4 is converted to brown precipitate of MnO2 during the reaction, which also forms the basis for a Bayer test of alkenes. Rather, the formation of MnO2 within the reaction medium is indicative of the reaction proceeding. Now, next point, non-terminal alkenes can be converted to 1,2-diols, ketols, or 1,2-diketones by the choice of appropriate conditions. Here again, we have taken the reagent. It is used in alkaline medium. If the addition is syn and the stereochemistry of the alkene is over here E or trans, then obviously we will say it will lead to the formation of DL pair. So this compound and that compound will be having enantiomeric relationship to each other. However, if the alkene is Z or cis, then it leads to the formation of a meso compound, which will be having either a center of symmetry or a plane of symmetry. As we can see in this case of molecule, if we connect this OH with that OH, then over here there is a point which we can consider to be the inversion point, and any molecule having an inversion point or a plane of symmetry is a meso compound. Now over here we have a cyclooctaene in which we are using KMnO4 along with a phase transfer catalyst, and here as we can see, since the stereochemistry over here is cis, so it leads to the formation of a meso compound which will be having a plane of symmetry passing right through these two bonds as I am showing, and that is how it will take place. PTC means over here phase transfer reagent. So if you're using again a cyclohexene, again a meso compound is formed over here. So there is the plane of symmetry.